sklearn cross-decomposition. Description cross-decomposition methods in scikit-learn aim to extract relationships and common variations between two or more datasets. These methods are particularly useful when the datasets are related but not perfectly aligned. They seek to find a set of common components that capture the shared information, allowing for dimensionality reduction, feature extraction, and better understanding of the underlying relationships. Inputs. Input 1x. This is typically a matrix or array representing the first dataset. Each row represents a sample and each column represents a feature. Input 2y. This is the second dataset. Structured similarly to x. It could be another set of features, different measurements, or even target values for supervised learning tasks. Outputs. Output 1x transformed, a new representation of the first dataset, transformed onto the extracted components. Output 2y transformed, a transformed representation of the second dataset, corresponding to the shared variations. Steps. Step 1 Decomposition. The algorithm analyzes the input datasets to find a set of common components. This is often achieved through techniques like singular value decomposition (SVD) or non-negative matrix factorization (NMF). Step 2 Projection. The original datasets are projected onto the extracted components, resulting in lower dimensional representations that highlight the shared information. Metrics. Metric 1 Explained variance ratio. This metric quantifies the proportion of variance in the original datasets that is captured by each component. Higher values indicate that the components are effectively capturing the shared information. Metric 2 Mean Squared Error (MSE) in supervised learning tasks. MSE can be used to assess how well the transformed data predicts the target values. Visualization plots. Visualization plot 1 Scatter plot. A scatter plot of the transformed data points can reveal clusters or patterns in the shared variation. Visualization plot 2 Scree plot. This plot shows the explained variance ratio for each component, allowing you to identify the most informative components in the point of diminishing returns in dimensionality reduction. Fine-tune parameters. Parameter 1 N components. This parameter controls the number of components extracted. Higher values capture more variance but can lead to overfitting. Parameter 2 Regularization parameters. Some methods offer regularization parameters to prevent overfitting or to enforce specific properties on the extracted components. Uncertainty methods. Uncertainty method 1 Bootstrapping. This method involves resampling the data multiple times and performing the cross-decomposition on each resample. The variability in the extracted components can be used to estimate uncertainty. Uncertainty method 2 Cross-validation. By splitting the data into training and testing sets, cross-validation can assess the generalization performance of the model and provide insights into its robustness. Challenges and fixes. Challenge 1 High dimensionality. If the input datasets have a large number of features, the cross-decomposition algorithm may struggle to find meaningful components. Sample use case that resulted in challenge 1 Working with microarray data with thousands of genes. Fixes to challenge 1. Feature selection. Apply dimensionality reduction techniques like PCA or feature selection methods to reduce the number of features before applying cross-decomposition. Regularization. Use regularization techniques to penalize complex models and prevent overfitting. Challenge 2 Data scaling. Different scales in the input datasets can affect the extracted components. Sample use case that resulted in challenge 2 One dataset has features in the range of 0 to 1, while the other has features in the range of 100, 1000. Fixes to challenge 2. Standardization scale the input datasets to have zero mean and unit variance before applying. Cross-decomposition. Feature scaling use other scaling methods, like min-max scaling, to ensure that all features have a similar range. sklearn cross-decomposition CCA. Input 1 explain in detail two sets of multidimensional data, where each set represents different views or perspectives of the same underlying phenomenon. For instance, one set might be gene expression data, and the other might be clinical data. Input 2 explain in detail the data is expected to be in the form of NumPy arrays or pandas. Data frames, where each row corresponds to a sample and each column corresponds to a feature. Output 1 explain in detail a set of canonical variables, also known as canonical components, for each input data set. These variables represent linear combinations of the original features and capture the maximum correlation between the two sets of data. Output 2 explain in detail the correlation coefficients, also known as canonical correlations, between the corresponding canonical variables, indicating the strength of the relationships between the data sets. Step 1 explain in detail the CCA algorithm finds a set of linear transformations for each input data set. These transformations aim to project the data into lower dimensional spaces, where the canonical variables' linear combinations of the original features maximize the correlation between the two projected data sets. Step 2 explain in detail the transformations are computed by solving a generalized eigenvalue problem, where the eigenvalues represent the squared canonical correlations and the eigenvectors correspond to the weights of the linear transformations. Metric 1 explain in detail canonical correlations between the canonical variables. Provide a measure of the strength of association between the two data sets. Metric 2 explain in detail explained variance, which represents the proportion of variance in the original data that is captured by the canonical variables. Visualization plot 1 explain in detail scatter plots of the canonical variables can be used to visualize the relationships between the two data sets. Visualization plot 2 explain in detail bar plots can be used to visualize the weights of the linear transformations, highlighting the relative contributions of different features to the canonical variables. Parameter 1 explain in detail n components. This parameter specifies the number of canonical variables to extract. Typically, a smaller number of components is sufficient to capture the most significant relationships between the data sets. Parameter 2 explain in detail regularization. This parameter introduces regularization to the CCA model, which helps to prevent overfitting and improve the stability of the solution. Uncertainty method 1 explain in detail bootstrapping can be used to estimate the uncertainty of canonical correlations and the weights of the linear transformations. Uncertainty method 2 explain in detail cross-validation can be used to evaluate the model's performance on unseen data and estimate the generalization error. Challenge 1 explain in detail high dimensionality of the input data sets can lead to computational challenges and potentially unstable results. Sample use case that resulted in challenge 1 when analyzing high-dimensional genomic data. The number of features genes can be significantly larger than the number of samples, leading to computational complexity and potential overfitting. Fixes to challenge 1 dimensionality reduction techniques, e.g., PCA. Feature selection can be applied to the input data sets before performing CCA. reducing the number of features and improving computational efficiency. Challenge 2. Explain in detail nonlinear relationships between the data sets may not be adequately captured by CCA, which is a linear method. Sample use case that resulted in Challenge 2. Analyzing data from different biological experiments, where the underlying relationships are not strictly linear, might require nonlinear methods for optimal analysis. Fixes to Challenge 2. Consider nonlinear methods like kernel CCA or other nonlinear dimensionality reduction techniques to capture complex relationships between the data sets. sklearn cross decomposition PLS canonical. Description: PLS canonical is a method for canonical correlation analysis, which seeks to find linear combinations of two sets of variables that are maximally correlated. It is a supervised learning technique that can be used for dimensionality reduction, feature selection, and prediction. Inputs: X a 2D array of shape n samples. N features X representing the first set of variables. Y a 2D array of shape n samples. N features Y representing the second set of variables. Outputs: X weights a 2D array of shape n features X. N components representing the weights for the linear combinations of the first set of variables. Y weights a 2D array of shape n features Y. N components representing the weights for the linear combinations of the second set of variables. X scores a 2D array of shape n samples. N components representing the scores for the first set of variables. Y scores a 2D array of shape n samples. N components representing the scores for the second set of variables. Steps: calculate the covariance matrices of X and Y. Calculate the correlation matrix of X and Y. Find the eigenvectors and eigenvalues of the correlation matrix. The eigenvectors with the largest eigenvalues represent the canonical variates, which are the linear combinations of X and Y that are maximally correlated. The weights for the canonical variates are the X weights and Y weights. The scores for the canonical variates are the X scores and Y scores. Metrics: canonical correlations, the correlations between the canonical variates. These values measure the strength of the relationship between the two sets of variables. Explained variance, the proportion of variance in each set of variables that is explained by the canonical variates. Visualization plots: scatter plots of the canonical variates. These plots can be used to visualize the relationship between the two sets of variables. Loadings plots: these plots show the weights for the canonical variates, which can be used to identify the variables that are most important for each canonical variate. Fine-tune parameters: n components, the number of canonical variates to extract. Scale: whether to scale the data before performing the analysis. Copy: whether to copy the data before performing the analysis. Uncertainty methods: bootstrapping. This method can be used to estimate the uncertainty in the canonical correlations. And loadings. Challenges and fixes. Challenge 1: the data may be highly correlated, leading to unstable results. Sample use case that resulted in Challenge 1: a dataset with multiple highly correlated features. Fixes to Challenge 1: use a regularization technique, such as ridge regression. Select a smaller number of components. Challenge 2: the data may be nonlinear, which can lead to poor performance. Sample use case that resulted in Challenge 2: a dataset with a nonlinear relationship between the two sets of variables. Fixes to Challenge 2: use a nonlinear method, such as kernel canonical correlation analysis. Apply a nonlinear transformation to the data before performing the analysis. sklearn, cross decomposition, PLS regression. Description. PLS regression is a supervised dimensionality reduction technique that finds latent variables, components in both the predictor X and response Y variables, aiming to explain the maximum covariance between them. It differs from principal component regression PCR by using the information from both X and Y for component extraction, leading to better prediction when the variables are highly correlated. Inputs: X a 2D array of predictor variables, N samples, X n features. Y a 2D array of response variables, N samples, X n targets. Outputs: YPRED the predicted response values based on the fitted model. XCOS the scores of the predictor variables on the latent variables N samples X n components. YSCOS the scores of the response variables on the latent variables N samples X n components. COA the coefficients of the linear model that relates the latent variables to the response variables. Steps: calculate the covariance matrix between X and Y. Find the singular value decomposition SVD of the covariance matrix. Extract the top n components' singular values and their corresponding vectors. Project both X and Y onto the subspace spanned by the extracted singular vectors, resulting in the XCOS and YSCOS. Fit a linear model using the XCOS to predict the YSCOS. Metrics: R squared R2 represents the proportion of variance in the response variables explained by the model. Mean squared error MSE measures the average squared difference between the predicted and actual response values. Root mean squared error RMSE the square root of MSE, providing an interpretable scale for the error. Visualization plots: scatterplots of XCOS vs YSCOS to visualize the relationship between the latent variables. Scree plots showing the singular values, indicating the importance of each component. Fine-tune parameters: N components the number of latent variables to extract. Determining the dimensionality reduction. Scale whether to scale the data before performing PLS. Influencing the impact of variable scales on the results. Copy whether to copy the data before fitting. Allowing for in-place modification of the original data. Maxiter maximum number of iterations for the PLS algorithm. Uncertainty methods. Bootstrapping resampling the data with replacement to estimate the variability of model. Parameters and predictions. Cross-validation splitting the data into multiple folds and training the model on different combinations of folds to assess its generalization performance. Challenges and fixes. Challenge 1: multicollinearity in predictor variables can lead to unstable PLS results. Sample use case that resulted in challenge 1: when predictors are highly correlated, the PLS model may overfit the data and perform poorly on unseen samples. Fixes to challenge 1. Use variable selection techniques to remove redundant predictors. Regularize the PLS model with methods like ridge regression. Challenge 2: choosing the optimal number of components can be subjective. Sample use case that resulted in challenge 2: selecting too many components can lead to overfitting, while selecting too few can result in underfitting. Fixes to challenge 2. Use cross-validation to evaluate the model performance with different numbers of components. Examine the Scree plot for an elbow point, indicating a good trade-off between dimensionality reduction and explained variance. sklearn cross decomposition PLS-SVD. Description: partial least squares with singular value decomposition PLS-SVD is a dimensionality reduction technique that aims to find latent variables that explain the maximum covariance between two data matrices, X and Y. It's a powerful tool for analyzing data where variables are highly correlated or where the goal is to identify common patterns in both datasets. Inputs: X, a matrix of predictor variables, N samples. N features X. Each row represents a sample, and each column represents a predictor variable. Y, a matrix of response variables, N samples. N features Y. Each row represents a sample, and each column represents a response variable. Outputs: X scores the scores of the X data projected onto the latent variables. This represents the variations of X explained by the model. N samples, N components. Y scores the scores of the Y data projected onto the latent variables. This represents the variations of Y explained by the model. N samples, N components. X loadings, the weights for each predictor variable in the X data that contribute to the latent variables. N features X. N components. Y loadings, the weights for each response variable in the Y data that contribute to the latent variables. N features Y. N components. Steps. Step 1: compute the covariance matrix between the X and Y data. Step 2: perform singular value decomposition (SVD) on the covariance matrix. Step 3: extract the top component's latent variables based on the singular values, which capture the maximum covariance between X and Y. Step 4: project the X and Y data onto the latent variables to obtain the scores and loadings. Metrics. R2X, the proportion of variance explained in the X data by the model. R2Y, the proportion of variance explained in the Y data by the model. Visualization plots. Scree plot, a plot showing the singular values, which helps identify the optimal number of components to retain. Scores plot, a scatter plot of the X scores and Y scores, visualizing the relationship between the X and Y data in the lower dimensional space of the latent variables. Loadings plot, bar plots of the X loadings and Y loadings, revealing the importance of each feature in contributing to the latent variables. Fine-tune parameters. N components, the number of latent variables to extract. This parameter controls the dimensionality reduction. Scale, whether to scale the X and Y data before performing PLS-SVD. Scaling can improve the performance if the variables have different scales. Algorithm. The algorithm used for SVD can be RPAC for large matrices or SVD for smaller matrices. Uncertainty methods. Bootstrapping, repeatedly sampling the data with replacement and performing PLS-SVD on each bootstrap sample to estimate the variability of the model parameters. Cross-validation, splitting the data into training and validation sets, and using the validation set to evaluate the model's performance. Challenges and fixes. Challenge 1: overfitting. The model may overfit the data if too many components are selected or if the data is noisy. Sample use case that resulted in challenge 1: a model with too many components might perfectly fit the training data but fails to generalize well to new data. Fixes to challenge 1. Use cross-validation to select the optimal number of components. Regularize the model using techniques like L1 or L2 regularization. Use a simpler model with fewer components. Challenge 2: collinearity. Highly correlated variables in the X data can lead to instability in a model. Sample use case that resulted in challenge 2: when multiple predictor variables are highly correlated, the model might become sensitive to small changes in the data, leading to unstable results. Fixes to challenge 2. Perform feature selection to remove highly correlated variables. Use regularization techniques to penalize large weights for highly correlated variables. Consider using other dimensionality reduction techniques such as principal component analysis (PCA) before applying PLSSVD.